G'day, fellow science enthusiasts, and welcome. Have you ever looked up at the night sky? I mean, really looked up. You see that vast, dark expanse glittering with countless stars. Each one of those twinkling lights is a sun, just like our own. Many of them have planets orbiting around them. It's a breathtaking sight, isn't it? It fills you with a sense of wonder, but it also makes you ask a very big question. A question humans have been asking for thousands of years. Are we alone in this unimaginably huge universe? This question has captured our imagination for centuries. It's the stuff of legends, myths, and campfire stories. It has inspired countless books and movies. We've dreamt up all sorts of alien beings. For most of human history, this question was purely philosophical. It was a thought experiment, something to ponder without any real way of finding an answer. But today, we stand on the brink of a new era. Science has given us incredible new eyes. These eyes can see across light years of space. We are no longer just guessing. We are actively searching. We are developing amazing methods to hunt for clues of life on other planets. All right, let's get down to the nitty-gritty. We've talked about using light as a messenger. But what does that actually mean? The light we see with our eyes, what we call visible light, is just one tiny slice of a much bigger picture. It's part of something called the electromagnetic spectrum. Imagine you're at the beach. You feel the warmth of the sun on your skin. That's infrared light, a type of light we can't see, but can definitely feel as heat. You've all seen a rainbow, right? What's happening there is that sunlight, which looks white to us, is being split apart by raindrops. Just as raindrops can split sunlight, scientists have created instruments that can do the same thing with incredible precision. These instruments, called spectrographs, can take the light from a distant star and spread it out into a detailed spectrum, a cosmic rainbow. It turns out that every single element in the universe interacts with light in its own unique way. Think of it like a fingerprint. When light passes through a gas, certain colors or wavelengths are absorbed by the atoms and molecules in that gas. It's like they cast a specific shadow in the rainbow of light. By looking at which colors are missing from the starlight, we can identify exactly what gases are present. It's an unambiguous code. Scientists first used spectroscopy to study our own sun. They found familiar signatures of hydrogen and other elements, but also found a set of lines that didn't match any known element. They correctly guessed it was a new element, and they named it helium after Helios, the Greek god of the sun. Helium was discovered on the sun before it was ever found on Earth. For decades, astronomers have pointed their spectrographs at all sorts of cosmic objects, performing remote chemical analysis of objects they could never hope to visit directly. Before we can analyze an exoplanet's atmosphere, we have to find the exoplanet in the first place. This is a massive challenge. Trying to see an exoplanet directly is like trying to spot a firefly sitting next to a colossal searchlight from kilometers away. Because direct imaging is so difficult, astronomers had to get very clever. They developed indirect methods to find these hidden worlds. The very first exoplanet orbiting a sun-like star was only confirmed in 1995. That's well within the lifetime of many people watching this. One technique is called the radial velocity method, or the wobble method. When a planet orbits a star, it's not just the planet that moves. The star moves too, performing a tiny celestial wobble. The transit method is beautifully simple. If a planet's orbit is lined up just right, it will pass directly in front of its star, causing a very slight temporary dip in the star's brightness. Missions like NASA's Kepler Space Telescope stared at over 150,000 stars for 4 years, looking for those telltale periodic dips in light. Here is where it all comes together. When that planet passes in front of its star, a tiny sliver of starlight shines directly through the upper layers of the planet's atmosphere. It's like the star is backlighting the planet for us. The gases in that atmosphere will absorb some of that light, leaving their unique fingerprints imprinted on the starlight. By comparing the star's light before, during, and after the transit, we can isolate the atmospheric signature. This is precisely what the James Webb Space Telescope was built to do. It is designed to be exceptionally sensitive to infrared light, where many important molecules leave their strongest spectral fingerprints. So what exactly are we looking for? We're searching for chemical clues in the atmosphere that are so unusual, so out of place, that the most plausible explanation is the presence of life. We call these clues biosignatures. On Earth, the large amount of oxygen in our atmosphere is a powerful biosignature. It's almost entirely produced by living things through photosynthesis. Without life constantly pumping it out, our oxygen would quickly disappear. Perhaps the most powerful biosignature isn't a single gas, but a strange combination. We have oxygen, which is highly reactive, coexisting with methane, something that oxygen should destroy. This atmospheric disequilibrium is a blatant planet-scale sign of biology at work. One of the very first planets to have its atmosphere studied was HD 209458b, nicknamed Osiris. In 2001, scientists made a groundbreaking discovery, the first detection of an element in an exoplanet atmosphere: sodium. Because Osiris is so close to its star, its atmosphere is literally boiling off into space. We were witnessing a world being slowly evaporated by its own sun, a dramatic process we had never seen before. It was a monumental proof of concept. It showed that transit spectroscopy actually worked, setting the stage for everything that was to come. One of the most fascinating worlds Webb has studied is K218b, a sub-Neptune about 120 light-years away. Webb's observations confirmed water vapor and detected significant amounts of methane and carbon dioxide, but the most surprising finding was a hint of dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton. Finding it on K218b would be a potential biosignature of the highest order. However, the science team has been extremely cautious, stating that this detection is tentative and needs more verification. It's a cliffhanger in our cosmic detective story. A new generation of colossal ground-based telescopes is under construction. The extremely large telescopes will have mirrors stretching 39 meters across, gathering more light than all existing large telescopes combined. These telescopes will use adaptive optics. Powerful lasers create artificial guide stars, and computers adjust flexible mirrors thousands of times per second to cancel out atmospheric blurring. It effectively untwinkles the stars. In space, scientists are planning the Habitable Worlds Observatory, designed specifically to detect and characterize dozens of potentially Earth-like exoplanets using advanced coronagraphs to block starlight. One radical concept is the Starshade, a massive spacecraft that would fly tens of thousands of kilometers in front of a telescope, casting a perfect shadow to block starlight while allowing planetary light to pass through. This would allow us, for the first time, to directly image small rocky planets in habitable zones and capture the spectrum of their atmospheres. This is the ultimate goal. The future lies in combining all these approaches, giant ground telescopes working alongside space observatories, some finding planets while others characterize their atmospheres. We stand at a unique moment in human history. For millennia, the question, "Are we alone?" was a philosophical musing, a campfire story. It was posed to the silent, glittering heavens with no real expectation of an answer. But now, the silence is being broken. We have, for the first time, built the tools and developed the techniques to seek a scientific, data-driven answer to this most profound of questions. It's a staggering transition from speculation to observation. We are no longer just asking. We are listening, and the universe is beginning to talk back. The path ahead is filled with challenges. Interpreting the faint whispers of light from worlds trillions of kilometers away is one of the hardest things scientists have ever attempted. But the relentless spirit of human curiosity, the same spirit that led our ancestors to explore new continents, is now guiding our telescopes toward new worlds. The potential discovery of life beyond Earth would be a watershed moment for our species. It would fundamentally reframe our place in the universe. Whether we find a galaxy teeming with life or discover that we are profoundly alone, the answer will be equally transformative. The search is more than scientific. It's a search for our cosmic family tree. We are the generation that gets to start this search in earnest. The next discovery could be just one observation away, waiting in the light from a distant star. The great cosmic question remains unanswered for now, but for the first time we are not just asking, we are listening. And the universe is beginning to talk back.